The Sun represents the most substantial mass concentration in our solar system, serving as the gravitational anchor that holds planets, asteroids, comets, and other celestial bodies in their orbits. Understanding the Sun's mass provides crucial insights into stellar physics, planetary dynamics, and the evolution of our cosmic neighborhood. The Sun's immense mass influences everything from nuclear fusion in its core to the orbital mechanics of distant Kuiper Belt objects, making it one of the most important physical parameters in our local universe. The Sun possesses a truly colossal mass that dominates our solar system. Current measurements place the Sun's mass at approximately 1.99 quindecillion kilograms, which is more readily understood when expressed as 1 nonillion, 990 octillion kilograms. To put this enormous figure into perspective, the Sun's mass is about 333,400 times greater than Earth's mass. This means that it would take over 300,000 Earths to equal the mass of our star. Another way to conceptualize this is to consider that the Sun accounts for approximately 99.86% of all mass in the solar system. Nearly everything in our cosmic neighborhood, all planets, moons, asteroids, comets, and dust, collectively represent just 0.114% of the solar system's mass. The Sun's enormous mass is concentrated in a spherical volume with a diameter of about 1.39 million kilometers, 864,600 miles, which is 109 times the diameter of Earth. Despite this massive size, the Sun's average density is only about 1.41 grams per cubic centimeter, 1,400 kilograms per cubic meter. This density is relatively low compared to Earth's average density of about 5.51 grams per cubic centimeter, meaning the Sun is only about 1.4 times denser than water. This seemingly contradictory combination of enormous mass but relatively low density occurs because the Sun is composed primarily of hydrogen and helium, the two lightest elements, in a gaseous and plasma state rather than solid form. The composition of the Sun's mass plays a fundamental role in its behavior and evolution. The Sun consists primarily of hydrogen, which accounts for approximately 73% of its mass. Helium comprises about 25% of the Sun's mass, with all other elements, collectively termed metals in astronomical parlance, making up less than 2% of the total mass. Among these heavier elements, oxygen contributes roughly 1% of the Sun's mass, while carbon, neon, and iron each account for about 0.3%, 0.2%, and 0.2%, respectively. This composition differs significantly from that of rocky planets like Earth, which are predominantly composed of heavier elements. The Sun's elemental makeup reflects its formation from the primordial material of the solar nebula, which preserved much of the original composition of matter created in the Big Bang, supplemented by heavier elements produced by previous generations of stars. Interestingly, the Sun's composition has not remained static throughout its lifetime. The original chemical composition of the Sun, when it formed approximately 4.6 billion years ago, was estimated to be about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. Over billions of years of nuclear fusion, the Sun has gradually converted some of its hydrogen into helium, particularly in its core region. As a result, the proportion of helium within the core has increased from about 24% to approximately 60%. This ongoing transformation represents a fundamental aspect of the Sun's mass evolution. The Sun's mass is not evenly distributed throughout its volume. Instead, it exhibits a highly structured density profile, with mass heavily concentrated toward the center. The core of the Sun, extending from the center to about 20 to 25% of the solar radius, contains the densest material, with densities reaching up to 150 grams per cubic centimeter, about 150 times the density of water. This extreme density in the core results from the enormous gravitational pressure exerted by the overlying layers of the Sun. The immense mass of the Sun creates tremendous pressure and temperature conditions at its center. The core temperature reaches approximately 15.7 million Kelvin, compared to the relatively cool surface temperature of about 5,800 Kelvin. These extreme conditions are direct consequences of the Sun's mass and are essential for enabling nuclear fusion processes that generate energy. Beyond the core, the Sun's density decreases progressively through the radiative zone and convective zone until reaching the visible surface, photosphere, where the density is much lower. This density gradient is crucial for understanding how energy generated in the core is transferred outward through the Sun's interior. The mass distribution within the Sun also influences its rotation patterns, with recent analysis suggesting that the core rotates faster than the surrounding radiative zone. The Sun's enormous mass serves as the fuel reservoir for its energy production through nuclear fusion. In its core, the Sun fuses about 600 billion kilograms of hydrogen into helium every second. Through this process, approximately 4 billion kilograms of matter are converted directly into energy each second. This conversion follows Einstein's famous equation E=mc², where a small amount of mass yields an enormous amount of energy. Despite this seemingly rapid rate of mass consumption, the Sun's tremendous total mass means it can sustain this process for billions of years. Over its approximately 4.6 billion years of existence thus far, the Sun has converted around 100 times the mass of Earth into energy. Yet this represents only about 0.03% of the Sun's total mass. This small fractional change underscores the Sun's capacity to maintain stable energy production over astronomical timescales. The power output generated by the Sun's mass conversion is astonishing. The Sun releases energy at a rate of about 384.6 yottawatts, or approximately 9.192 x 10,000 megatons of TNT per second. This tremendous energy output is what sustains life on Earth and powers the entire solar system. However, when considered in terms of energy produced per unit volume, the power density at the center of the Sun's core is approximately 276.5 watts per cubic meter, comparable to the power density inside a compost pile. The Sun's immense power output results primarily from its enormous size, rather than an exceptionally high energy density. The Sun's mass creates the perfect conditions for nuclear fusion through the proton-proton chain reaction, which is the dominant energy production mechanism in stars like our Sun. In this process, hydrogen nuclei, protons, combine to form helium nuclei, releasing energy in the process. The core's enormous pressure and temperature conditions, direct consequences of the Sun's mass, enable these fusion reactions to overcome the electrostatic repulsion between positively charged protons. The proton-proton chain occurs approximately 9.2 undecillion times each second in the core, converting about 37 decillion protons into alpha particles, helium nuclei, every second. However, each individual proton takes, on average, about 9 billion years to fuse with another proton. This remarkably long time frame highlights why the Sun can maintain stable energy production for billions of years, despite its continuous mass-to-energy conversion. Currently, about 99% of the Sun's energy is generated within the innermost 24% of its radius, with almost no fusion occurring beyond 30% of its radius. The remaining mass of the Sun primarily serves to maintain the tremendous gravitational pressure required for fusion and to transfer the energy produced in the core outward through radiation and convection. As the Sun ages, the fusion rate in its core operates in a self-correcting equilibrium tied directly to its mass. If the fusion rate increases slightly, the core heats up and expands against the weight of the outer layers, reducing density and subsequently decreasing the fusion rate. Conversely, if fusion slows, the core cools and contracts, increasing density and fusion rate. This mass-dependent feedback mechanism helps maintain the Sun's stability over billions of years. The Sun's mass has undergone subtle but significant changes since its formation approximately 4.6 billion years ago. The most notable change has been the internal redistribution of mass as hydrogen fuses into helium in the core. This process has not only altered the Sun's chemical composition, but has also affected the mass distribution within the Sun. Due to gravity, helium and heavier elements have gradually settled toward the center of the Sun over time. This gravitational settling has contributed to an increased concentration of helium within the core, which has grown from about 24% to approximately 60% of the core's composition. Meanwhile, the proportion of helium in the photosphere has decreased. with the metallicity reduced to about 84% of what it was in the protostellar phase before nuclear fusion began. While these internal transformations are significant, the total mass loss of the Sun has been relatively small throughout its main sequence life thus far. The 0.03% of mass converted to energy over 4.6 billion years represents a minor fraction of the Sun's total mass. The Sun also loses mass through the solar wind, a stream of charged particles ejected from the Sun's upper atmosphere, but this represents an even smaller contribution to mass loss during the main sequence phase. The future evolution of the Sun's mass will follow a more dramatic trajectory than its relatively stable past. The Sun is currently about halfway through its main sequence lifetime and will remain relatively stable for another 5 billion years. During this period, it will continue to gradually convert hydrogen to helium and increase in luminosity by about 1% every 100 million years due to the changing composition and structure of its core. When the Sun exhausts the hydrogen in its core in approximately 5 billion years, its evolution will accelerate dramatically. As the core contracts and heats up, hydrogen fusion will continue in a shell around the core, causing the outer layers to expand. The Sun will enter its red giant phase, during which it will swell to about 256 times its current size, with a radius of approximately 1.19 astronomical units. During the red giant branch phase, which will last about 1 billion years, the Sun will lose approximately 1/3 of its total mass through enhanced stellar winds. This significant mass loss will have profound implications for the orbits of planets in our solar system. Initially, Earth's orbit will expand to as much as 1.5 astronomical units due to the Sun's reduced gravitational pull. However, as the Sun expands, tidal forces and atmospheric drag will eventually cause Earth's orbit to decay, ultimately resulting in Earth being engulfed by the expanding Sun. After the red giant phase, the Sun will experience a helium flash, a sudden explosive ignition of helium fusion in its core. During this brief but violent event, approximately 6% of the core will be converted into carbon within minutes through the triple alpha process. The Sun will then shrink and spend about 100 million years burning helium in its core. When helium is exhausted, the Sun will expand again into the asymptotic giant branch phase. During this unstable period, lasting about 20 million years, the Sun will experience thermal pulses every 100,000 years, with rapid mass loss through stellar winds. These pulses will grow increasingly powerful, temporarily boosting the Sun's luminosity to as much as 5,000 times its current level. By the end of its life, the Sun will have shed nearly half of its original mass. The remaining material will form a planetary nebula surrounding a dense, hot core, a white dwarf, that will slowly cool over trillions of years. The Sun's immense mass generates a powerful gravitational field that shapes the structure of the entire solar system. According to Newton's law of universal gravitation, the gravitational force between two objects is directly proportional to the product of their masses. With its dominant mass, the Sun exerts the primary gravitational influence on all bodies in our system. At the Sun's photosphere, the gravitational acceleration, or surface gravity, is approximately 27.9 times that of Earth. This strong gravitational pull helps maintain the Sun's spherical shape despite its gaseous composition and rapid rotation. Without this gravity, the Sun would quickly disperse into space. The Sun's gravity also creates a pressure gradient within its mass. At the core, the weight of all overlying material produces tremendous pressure that compresses the core material to extreme densities. This pressure gradient from the center to the surface is in hydrostatic equilibrium with the outward pressure generated by the hot gas and radiation, maintaining the Sun's stable structure. Beyond shaping the Sun itself, the star's mass determines the orbits of planets, asteroids, and comets. According to Kepler's third law, the square of a planet's orbital period is proportional to the cube of its semi-major axis, with the proportionality constant dependent on the Sun's mass. This relationship means that the Sun's mass effectively determines the clock of the solar system, the timing of planetary orbits and seasonal variations. The Sun's mass dominates our solar system, but it is relatively modest compared to many other stars in the galaxy. The Sun is classified as a G-type main sequence star, informally called a yellow dwarf. Its mass places it in the medium range of stellar masses, more massive than the numerous red dwarf stars, but far less massive than giant and supergiant stars. Based on its absolute magnitude of +483, the Sun is estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs with lower masses. However, the Sun is more massive than approximately 95% of the stars within 23 light-years of Earth. This indicates that while the Sun is above average in mass compared to its nearest stellar neighbors, it is not exceptional when considering the full range of stellar masses in our galaxy. The Sun's mass directly influences its classification, lifespan, and energy production method. Stars with significantly higher masses burn their nuclear fuel much more rapidly and have correspondingly shorter lifespans, often measured in millions rather than billions of years. More massive stars also can fuse heavier elements in their cores due to their higher central temperatures and pressures. The Sun's intermediate mass allows it to sustain stable hydrogen fusion over approximately 10 to 11 billion years on the main sequence, providing the long-term stability that has allowed life to evolve on Earth. Stars with significantly lower or higher masses would create very different conditions for potential planetary systems. Determining the mass of the Sun has been one of the fundamental challenges in astronomy since the development of Newtonian mechanics. The primary method for measuring the Sun's mass relies on Kepler's laws of planetary motion and Newton's law of universal gravitation. By observing the orbital period and distance of Earth or other planets, astronomers can calculate the Sun's mass with high precision. The modern value for the Sun's mass has been refined through radar reflections from planets, which provide precise measurements of planetary distances and orbital parameters. The value of approximately 1.99 nonillion kilograms represents one of the most accurately known astronomical constants. The Sun's mass is so fundamental to astronomy that it serves as a standard unit of measurement. Astronomers commonly express the masses of other stars and even galaxies in terms of solar masses, where one solar mass equals the mass of our Sun. This practice reflects the Sun's role as a benchmark against which other cosmic objects are measured. The Sun's mass stands as one of the most consequential physical parameters in our cosmic neighborhood, directly influencing everything from nuclear fusion in the solar core to the orbits of the outermost planets. At approximately 330,400 times Earth's mass and comprising 99.86% of the solar system's total mass, the Sun creates the gravitational foundation upon which all planetary dynamics depend. The composition of this mass, predominantly hydrogen and helium with trace amounts of heavier elements, reflects both the primordial material from which the Sun formed and the nuclear processes that have gradually transformed its core over billions of years. As the Sun ages, its internal mass distribution and composition continue to evolve, with significant consequences for its structure, luminosity, and stability. Looking ahead, the Sun's mass will undergo much more dramatic changes during its red giant and asymptotic giant branch phases, ultimately losing about half its mass before ending its life as a white dwarf. These changes will profoundly reshape the solar system and determine the ultimate fate of Earth and other planets. Understanding the Sun's mass not only illuminates the workings of our own star, but provides crucial insights into stellar physics more broadly. As astronomical techniques continue to advance, our knowledge of the Sun's mass and its implications will undoubtedly be refined, enhancing our understanding of both our local cosmic environment and the universe at large.